Okay, so some of you missed the lessons last Thursday and Friday because you had art exams, etc. And because of that, you will have missed a bit of a chunk of P2, finishing off the waves and starting space. So to save you falling behind and having to try and learn it yourself, I thought you could work through this video, catch up on the work you've missed, and then hopefully you haven't missed out. So the first thing we did was we went back to this idea of a spectrum. Just turn the pen on for a minute. So we went through the 7 different types of waves again, as shown in this diagram, and I just explained it doesn't matter which way round it's drawn. If radio is at this end, then what we're talking about is the low frequency, long wavelengths, or if radio is drawn at the other end, it just goes the other way. A diagram like this can be put in either direction. The bits I pointed out on this and why we revisited it was actually the size of the waves. So when we're talking about these waves down here, we said they were really long wavelength, and I said they could be hundreds of meters long. Well, there you go, 100 kilometers long. So radio waves can be incredibly long and low energy waves. And when I originally drew these gamma waves on the board, I said it was impossible to draw them. So if you look at this, a wavelength of 10 to the minus 11 meters. So that would mean 100 million waves in a millimeter. So actually having some idea of the scales for the waves, you need to know. Then obviously you can put all 7 in order, from gamma, X-rays, ultraviolet, then you've got the visible light in the middle, infrared, microwaves and radio waves. Knowing them in order, absolutely essential. Being able to compare any of them, same. And then the speed. So the speed of light, 300 million meters per second. Or 300,000, if I draw a line there, kilometers per second. You're expected to know that speed. The other thing is, that is also not just the speed of light, it's the speed of X-rays. It's the speed of infrared. It's the speed of radio waves. All electromagnetic waves travel at that speed. Second thing we went on to was we wanted to revisit this idea. Why would a red apple appear to be red? But this time we were revisiting it from a point of view of the correct terminology. So, when light hits a material, it could be absorbed. Somebody last week in class said attracted. It's not attracted. If the light is taken in by the material, it's absorbed. If the light bounces off the material, it's reflected. And if the light passes through the material, that's what the word transmission means. So when we look at, from our eyes point of view, people drew this diagram, they could put any object in the middle, and the idea being that the white light from the sun contains the 7 different colours of the rainbow in the right order. And here what you talk about is 6 colours being absorbed and 1 colour here, red, being reflected. Then we moved on to a filter. Now, as you can see from this red filter, all 7 colours, the white light going into the filter, red is transmitted, whereas the other colours are being absorbed. So just explaining how a filter works. If you had a purple filter would transmit red and blue, and red and blue together would look purple. Remember, because this is a recording, you can pause it anytime you want. So if you're doing these diagrams or writing a little explanation, that's what I'd suggest you do as we go along. Just pause it whenever you want. We just went over quickly the fact that any of these, so I asked you before half term to compare. And I asked you to choose any colours or wavelengths, etc. So for example, I could ask you to compare microwaves and, I don't know, ultraviolet. Now from that, the first thing I would do is I'd go, oh, this is the radio end, so these are the, and this end gamma. So what I've got straight away in my head now is a picture, whereas these ones here have a long wavelength, because comparing, first of all, I'll point out the differences. Trying to write on this is hard. So the longer, my first point can be my microwaves have a longer wavelength than my ultraviolet. My second point, there's my long wavelength, can be that the microwaves have a lower frequency than my ultraviolet. Then I can point out microwaves have less energy than ultraviolet waves. So all I've done so far is point out differences, but the word compare in exams. By comparing, I have to give differences, which are easy, and we did that before. The new bit really was, what do they have similar? And the first thing is, they are all electromagnetic waves. And in class, what other people said is, they are both microwaves and ultraviolet, they're both transverse waves. They both travel through a vacuum. They don't need a carrier material like sound waves do. So now what I've managed to do is, because I've given 3 differences and 3 similarities, I've now compared the two together. So go back to your original comparison maybe and add on for the one you did, how are they similar? I gave people 1, 2, 3, 4, 5, 6, 7 minutes. 7 minutes because radio waves, we've already covered a lot of this. I just wanted to make sure we had something down for each one. You're expected to be able to give a use for each one. The only one we expanded on in class was the gamma waves. We'll come to that in a second. So radio waves used for transmitting signals for radio and television signals. Not used so much anymore now as they used to be terrestrial TV signals. Lots of things carried by cables now, optic cables, or sometimes by satellite signals, so microwaves. Microwaves, yes, one frequency of microwaves are used for cooking food, but actually the main use of microwaves is satellite communications and phones, mobile phones, etc. Infrared cameras, infrared heaters, etc. Visible light is used in fibre optic for communications, and that way, that's what our normal phone systems and the internet and stuff use around buildings and stuff. Fibre optic cables carrying signals extremely fast. Ultraviolet, energy efficient bulbs, sun tanning, etc. X-rays, really obvious, medical imaging and treatment. And gamma rays. Now the reason we did a little bit more about gamma rays was gamma rays are used down here, medical imaging fine, but kill tissue. So not only are gamma rays dangerous, and everyone seems to know the dangers of nuclear radiation, they can kill cells. When we use gamma rays as a really tight beam to kill a thing, it's called radiotherapy. So most people know that gamma waves and gamma rays can cause cancer, but actually they are a treatment for cancer. We also use gamma rays to sterilize. So in a hospital, when you're putting scalpels and different equipment inside people during an operation, you would have treated those with gamma rays first on the equipment, because gamma rays will kill any cells, therefore you can be guaranteed it's 100% sterile, whereas most sterilizing fluids will kill 99.9% of pathogens. Gamma rays would kill 100%. So again, pause, worth having a quick, and you can do that if you don't want to draw it as a table, which might take more time. Just do it as where you draw the wave, the electromagnetic spectrum, which I'm doing at the top at the moment. They get closer together, and you could list your 7 in order, which is great practice for learning it, and then underneath each one you could write down what a use is for it. So back to the same thing, even within light is a range, so there's a red range of wavelengths, then there's the orange range, and actually you'll end up with one, you could have quite a reddy orange, like a blood orange, and that's where the two are just crossing over together. But knowing that violet and red are at the ends of the visible spectrum, knowing that violet are the higher energy, higher frequency, shorter wavelength. Then we talked about why something might be shiny. So even a black surface could be shiny. And this represents a rough surface. And when the light rays, the blue ones here, when they hit the surface, they're scattering. And because they scatter, they go off at random angles. And that's, you get diffuse reflection. Now, what that means is the surface will look matte or dull. These matte or dull surfaces are usually the best ones for absorbing. Why might things be shiny? The smoother the surface, you get specular reflection, and that means it follows the law of reflection. So this ray here, the first one, bounces off at exactly the same angle. That angle there and that angle there are the same. It bounces off the same angle it hit. So that might be a mirrored or a shiny surface. So I'll give you time, well, I won't give you time. Take time to explain the difference between smooth, flat surfaces and rough surfaces. So here you have shiny, and here you have matte or dull. Then we went on to these 3 words, and again, I didn't ask anybody to write down the meanings. I got them to draw quick diagrams because a transparent material allows transmission of all the light. It doesn't cut anything out, etc. Therefore, it looks clear. Transparent is clear. You can clearly see through it. All the light comes through. Translucent is where you cut out some of the light. So a good example is tracing paper. But what you can see, you can clearly see the object. You can still see here that it's a candle, but it's not quite as clear as the transparent one. You've cut out some of the light. And opaque means it may not let light through, so opaque you can't see through it, or it can let through some of the light but actually not enough to tell what the object is. So here you wouldn't have a clue what's behind it, even though some light might be coming through. So, you'd probably want that as your bathroom window, an opaque surface. It might let some light through, but actually you wouldn't want them to be able to tell what the object is behind it. Then we moved on to something called, and this is a separate little title, black body radiation. Now I'm not going to spend long on this slide because this is a bit simple, but here we have, energy from the sun heats the horse up, the horse releases infrared, and we could see that with a camera, etc. And as long as you release the same amount as you absorb, well, what it's saying is it would stay at the same temperature. However, the horse will be generating heat itself, so it's not the best example. What we mean by a black body, a perfect black body. A black body is not a real object. A black body is an idealistic, it's theoretical feature, idealistic object. If this object absorbed all the electromagnetic radiation hitting it, if it absorbed every different wavelength of light, if it absorbed light from every angle, so whereas it might normally bounce off, this one doesn't, So basically any wave that hits it is absorbed. Now they've tried to make these, they've tried to make really matte surfaces, and they've played about with shapes and stuff. However, you can still see it. When we were discussing this in class, I was using the example of one of the students' jumpers. So the jumpers we wear in school are black. Just drawing a jumper because obviously you don't know what a jumper is because you've never heard of a jumper before. There you go, that's what a jumper is. And then the student would be inside the jumper like there, and they have legs. There you go. So that was actually the student I used in class. If this is a perfect black body, how would it appear to our eye? Well, nothing would be reflected off it. Therefore, it would just look like a gap in reality because everything would be absorbed. We'd just see a black space. Now, black surfaces we described as black was best because black surfaces were the best absorbers and black were the best emitters. So a black body would be the best at absorbing radiation, and it would also be the best at emitting radiation. So it would absorb everything that hit it, but actually if it was a warm object it would be brilliant, perfect more or less, at giving out the infrared from a radiation from a warm object. So what you're doing with black body is explaining what this idealistic object is. So in definition, it would absorb all electromagnetic radiation hitting it, all electromagnetic waves, and it would absorb it from every direction. So it wouldn't matter if it was just skimming it, it would still be absorbed. Nothing would be reflected. Okay, why is that useful to know? Why is that handy to know? It's how it's applied to the Earth as an object. So here we are with waves from the sun coming to the Earth and making it warmer. And here we are with the Earth sending waves off into space and cooling down. If the two are balanced, the Earth stays at the same temperature. However, because of greenhouse gases, because of the gases in the atmosphere here, they are reflecting some of the radiation back down. Therefore the Earth slowly gets warmer. Therefore the Earth is slowly increasing in temperature. And we just recapped from chemistry, everyone knows carbon dioxide is one of the main gases for global warming and contributing to that. The other main one is methane from rice farming and from cattle farming. The other main one is water vapour itself. And the problem is, the warmer the Earth is, the more H2O evaporates. Therefore there's more in the air, therefore causing it to get warmer. So it might be at some point we go past a point where we can actually reverse it. Then we moved on to this, the life cycle of stars, the sun, etc. So, in brief, first of all I told a story, then I let them write it up. So, in space there are great big clouds of dust, gas, and we're talking about billions and billions of times bigger than our solar system and our sun and everything included. Those are called a nebula. And inside a nebula, lots of little bits of material, oh, I don't like that colour pen, and bits of material here, and bits of material here, and little bits of material. Things are attracted together by gravity, and over a long period of time the gravity forces increases, because let's just say here for example, it keeps attracting more and more material, and this is, remember, a nebula is made up of dust and mostly gases. We'll explain where they all come from in a minute. So all this dust and gases and everything building up to big clouds of it with great big forces of gravity, what eventually starts to happen is the gravity is so strong that hydrogen atoms and hydrogen atoms can actually fuse together to make helium nuclei. That releases a large amount of electromagnetic radiation. It's called nuclear fusion. And we're talking about hundreds and hundreds of billions and 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 billions, I can carry on all day, of atoms fusing together. And once that reaction happens, we've actually created, within this nebula, we've actually created a star. And the one that you know most, I'll draw a picture of it so you recognise it because you've seen it. We've seen it twice this year. Hopefully we'll see it some more. We call it the Sun. And our Sun is a star. Our Sun is a great big nuclear fusion explosion. At the moment, our Sun is in, so this number 1 is the nebula. Number 2, our Sun is currently in its stable stage. And what's happening is there's a great big force outwards of the explosion, the nuclear fusion, and there's a great big force inwards of gravity. And they are both equal and opposite, hence why it's its stable stage. So what you're expected to do, make sure you're talking about gravity here and then the balance of the forces here when you write this up in a minute and when you pause it. Then what will happen is our Sun will start to run out of energy and it will run out of mass. So the forces outwards will be bigger than the forces inwards. So our Sun will eventually swell up into a much cooler, only a few thousand degrees, and it will something called a red giant. And our evidence for all of this is looking at millions of pictures through space telescopes and telescopes from the Earth and looking at all the different things we see out in space. And we see nebulas and we see stars starting to form in them, and sometimes the nebula is called a star nursery. So you can have a star starting here and here and here and here, and you have hundreds of stars starting in there. So they're not all close together. The nebula spans a massive area. So after we've swelled up to a red giant, we will then throw loads of this material on the outside off into space, and we will end up being a tiny little white dwarf. Now, how does this apply to any other learning you've done? Well, first of all, I'm going to write the number 56 here. And 56 on the periodic table is the element iron. And our current theories and our evidence suggest that the nuclear fusion inside the Sun and inside the red giant is enough to make elements. So if you go helium, hydrogen's made helium, and then you join the hydrogen and helium, everything will be a gas in there because of the temperature, but hydrogen and helium will form lithium, then beryllium, and so on and so on. All of the elements on the periodic table that everything's made of, up as far as 56, the theory is all of those can be made in normal stars in their normal cycle. Now, that white dwarf star, why it sit there for a long time or cool down, it's white, it's giving out a lot of heat because of and it's white because of the temperature it's burning at. However, all the material on the outside, lots of the material, is sent off into space. And eventually, over billions and billions of years, the spare material comes together with spare material from loads of other stars that were left over, and it forms clouds of gas and leftover stuff, forming new nebulas, which will then go round the cycle again. So all of this is called the star cycle. Now, this is what we think happens for a normal small star like our one over here in number 2. So we go nebula, nuclear fusion, the stable stage 2, the red giant 3, and the white dwarf 4. And back around the cycle again and again and again and again. However, what happens to bigger stars. And bigger stars burn faster. They last less time because they're burning so much hotter. We're coming on to that in a minute. So what I'd suggest you do is draw yourself a nice little diagram, and when you've done that, explain each stage in terms of gravity, and then explain number 56, iron. Stars are where elements are made, up as far as 56. When you finish that, continue. Okay, so we went on then to looking at the Milky Way. Didn't name it during the lesson, meant to. Now everyone's going to think it's just a chocolate bar. The Milky Way being our solar system, there's the word sun and there's a little yellow arrow pointing to a tiny little, we can't actually see it on this diagram, it's too small to see. But we know how far the nearest stars are. On this diagram it looks like the nearest stars are right next to each other, but we know they're billions and billions of miles apart. So the size of this Milky Way is incredibly hard to imagine. And then at the bottom, our solar system we think was formed 4.6 billion years ago. However, the universe itself 13.7 billion years ago. So our sun wasn't made then at the start. Our sun might well have been created in a nebula left over from spare materials from other stars that had already burnt out and exploded. That's there. I'm not going to go through it really. That's the planets in order, and obviously we also have comets, asteroids and satellites. Pause and add it down in detail if you don't know it, but I'm expecting most of you would know the planets in order by now, just from having been alive for 15, 16 years. This is very similar. This is just going through that diagram you drew a few minutes ago when I drew it in a cycle. So you've got the dust and gas in a nebula, attraction together, fusion happens, then it expands into a red giant, and then you've got parts that are left over forming gas and dust for the future. Again, this one just explaining how different elements, and here's one isotope of hydrogen and here's another isotope of hydrogen, and explaining how they can turn into helium, giving out some radiation, giving out some electromagnetic waves. And here's the diagram showing that the pressure outwards from the reaction and the gravity inwards are equal and opposite. So nothing really new on there, but might be useful to read through. And then I'd explain this. Ours is a small star. So looking over here at the left hand side of the diagram, ours is one of these stars over here, a small star. They use up their fuel slowly. So you've got your nebula, then you've got your main sequence star, then it turned into a red giant near the end of its life, and a white dwarf. It can become a black dwarf, so it cools down and just sits there in space, probably becomes part of a nebula in the future. And this is what happens for stars about the same size as our sun. However, when you look at bigger stars than our sun, instead of turning here, this is where it goes different. Instead of going that way, it goes this way. Instead of turning into a red giant, they turn into a red supergiant, much, 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 much bigger. What then happens is they explode. They turn into a supernova. And what can be left behind then is a very bright burning star called a neutron star, or a black hole, where the gravity is so strong not even the light can escape. However, hopefully the question you were asking yourself a minute ago was, well, if stars can make all the elements up as far as 56, where are the others made? So I'm just going to write here next to the supernova, when that red supergiant explodes in a supernova, that's when there are massive forces involved, and it creates all the elements greater than 56. So for example, where did the lead on the planet Earth come from? Well, the lead on our planet was made in the supernova of another star at some point during the universe's history. And that lead then ended up in a nebula and in the rock and the bits of rubbish that ended up making the Earth in the first place. So the fact there's lead on Earth means we know we're recycled out of a supernova from a massive star that exploded billions and billions and billions of years ago. Right. Then we went on to, and obviously you will have paused on that previous slide and hopefully done some notes as we go along. Then we went on to this. And what we talked about was the Doppler effect. And the Doppler effect is, if we have an ambulance or a police car and it's going along the road and it's going nee-no, 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 when it's approaching towards you, it increases the pitch, because you've not just got the sound waves travelling towards you, but because the car's coming forwards, it actually, let's try and draw it, instead of this, because it's coming towards you, it does this. It becomes more frequent, therefore a higher pitch. Here's you, and it becomes a higher pitch as it moves towards you. That means as it moves away from you, the wave gets dragged out. It becomes a lower pitch. So it should come towards you like this. Nee-no, nee-no, nee-no. And then as it passes you, I'll do it again. Nee-no, nee-no, nee-no. Nee-no, nee-no, nee-no. Because as it goes away from you, the wavelength gets longer. Now the same happens for light. With light, light is made of 7 colours. It's made from the red, orange, yellow, green, blue, indigo, violet. So those are 7 colours. Red at this end and violet at that end. That's the blue end of the spectrum, that's the red end of the spectrum. So if something giving out light was moving towards you, the light, so I'm going to write towards, it would go towards this end. There'd be less red and more blue. That's what this one up here is. Look at the top. If an object was moving towards you, there'd be more blue light in the mix. However, if an object was moving away from you, so I'm going to go down the bottom here, I go away. If an object was moving away from you giving out light, there would be more red and less blue, because that's turned into that, that's turned into that, that's gone there, and this end gets a bit more red. Now it still looks yellowy or white in the sky, but we analyse it, and I'll show you on the next slide in a minute. What that means is objects going away from us have a red shift. So what do we know? In our galaxy, where objects are not moving away from us, there's no redshift. In other galaxies, there is a redshift, and in distant galaxies, there's a big redshift. So what this means in space is everything is moving away from us. Everything is moving away from the Milky Way. Everything is moving away from our galaxy. That means the universe is getting bigger. And this idea of redshift is one of the reasons why we believe in the Big Bang. Everything is moving away. That's just a summary of what was on the last page. So if you want to stop on it, that's fine. So here is the universe a few billion years ago, and here is the universe now. the galaxies are moving away from each other, as if there was a big bang that caused everything to expand outwards from a original central point. And we are just sat there in one of these little galaxies made up of hundreds of millions of stars, and we're sat there going around one of those stars, our sun, as we move away from the other galaxies. This galaxy here next to us in a square is moving away from us, but this one over here on the other side of the universe is moving away from us quickly. So our best bit of evidence for the fact the galaxy is expanding is a red shift in the light emitted by other stars. Now, this is going through what's been discovered. This one is the second bit of evidence for the Big Bang. This is the one I want you to make note of. In the background, we have radio telescopes and radio and microwave telescopes. They pick up this cosmic microwave background radiation. This radiation is bouncing around all over the place, coming from every direction into our telescopes, like a massive, great big echo. But it's not an echo because this is microwave and radio wave radiation. But these longer wavelength radiations are bouncing around the universe as if there was a big explosion. So at some point an event happened, the Big Bang, which just sent so much radiation out into space that it's still bouncing around now. So that one is called CMBR, Cosmic Microwave Background Radiation. And redshift, RS, and that, they are the two strong bits of evidence to suggest the universe is getting bigger, it's spreading out, and that it started in one place with a Big Bang. And then at the bottom here it says there is still much we do not understand about the universe. So, is it going to continue on forever? Will it collapse back again due to gravity to the same point? Beyond our universe, are there a series of other universes, multiverse? And does life exist on other planets? I can actually answer that for you. Maybe.